Good evening, everyone. Hello. How is everyone doing? Do you have a nice time? Good. Good. We'll have a nice break later for networking and discussions also after our two talks. Welcome to Vienna Deep Learning Meetup. This is the 64th edition, so we have had quite some meetups since 2016. Who are we? So I'm Tom Lidy. I work now for iGroove. I organize these meetups together with four people, René, Jan, Alex, and Pavel. Alex is just coming in. Hello. And Pavel also. Yeah, there you are. We try to give you interesting talks and insights around the topic of deep learning. So that's our main topic, deep learning. But we, domain-wise, we go in all different directions. As you see, tonight we have the topics of cognitive strategies, cognitive learning, and also GenAI for images. And if you know interesting talks, interesting speakers, let us know. We'll have in the networking we call for future venues and speakers. Maybe quick check, who is here tonight for the first time at Vienna Deep Learning Meetup? Okay, thanks for coming. Hope you become a regular visitor. I'm here with Georg Heiler from Magenta, and he's our host tonight. And thanks for organizing the local, these rooms, splendid venue, and the drinks and snacks, the buffet we're gonna have in the break.
Thanks for a kind introduction. And on behalf of Magenta, I can send you a warm welcome here in our big Veranstaltungssaal. I have a couple of things to ask you. So once you have emptied the bottles, please put them downstairs into the boxes so it's easier to clean up later. But that's pretty much everything you have to take care of. So who are we? Well, I guess everyone knows we're selling TV, broadband and mobile networks. But what are we doing for real? We're basically connecting people, allowing them to even remotely connect to their loved ones and share emotions. That being said, what are we doing with data? Well, on one side, we are cloudifying a lot of things in our data platform. I have a couple of interesting topics to talk about there. Actually, on the 9th of April, we will have an in-depth session at the next data engineering meetup here in this room again. And then we have a couple of AI use cases. Maybe these are more interesting for this round. It's mostly about analyzing data from call center recordings, figure out how happy our customers are to then improve our services, basically. That being said, I will hand the word back to Tom. And if you want to know anything more about what we're doing, reach out to me or a couple of the team that are around here. We have some open positions for hiring. You will find them on the website.
Thank you very much, Georg. It's really nice to be here with a large room, large meetup, so it deserves a venue like Magenta. This is our program tonight. We have two talks that are about 45 minutes. Our first speaker is Gosztolai with the neural basis of cognitive strategies. Then we do roughly half an hour break with a few announcements before and go into the second talk that is GenAI for images in 2025 by Mouhannad and Julius Duin. This is the moment where you can announce whether you have a new exciting project or positions open, or you want to announce an event that is coming up that is interesting to our community around deep learning AI. If you want, you can do this also spontaneously. The better way to do is to contact us beforehand. For example, before our next meetup on 19th of March, contact at VDLM AT if you want to announce open positions, events, etc. Anastasia has done so, and I'm going to call her up on stage to tell us about this.
Thank you, Tom. I just wanted to invite you to our seminar about machine learning, security, privacy, and legal aspects, which is organized by AI security and privacy experts from SBA Research and legal experts from Research Institute. So this seminar, you will have opportunity to learn about AI Act and its implications for your businesses, about security and privacy threats in AI, and of course, you will get an insights of defense strategies, what you need to do to make your AI secure and private, so your product in which you use your AI is also secure and private. Please register using the link, and if you have any questions, feel free to ask me about privacy and security aspects. I'm working in SBI research. I actually gave also a talk last year on deep learning seminar about differential privacy. So yeah, please feel free to connect, and I will be happy to see you at our seminar.
Thank you, Anastasia. Okay, and this is just a pointer. We usually put all the slides of our speakers and talks from the past, so 63 earlier meetups, up here on this GitHub page, github.com/vdlm. I think we are late with a few slides. Pardon for that, but most of the resources you find there from the past meetups if you're interested in a particular topic that we had in the past. And yeah, now let's get into the break. Georg, thanks to you. Sorry. One more announcement. Yeah, Rahim.
Hello, my name is Rahim and I'm from Stability. We have 2 open positions, like one as a senior data engineer and the other one is a research scientist. So if you ever worked with text to image or text to video generation, which is probably the next talk, we have 2 open positions. Just talk to me in the break. Thank you.
Cool. That's exactly what the meetup is about. Not only about talks, but also connecting and finding new opportunities. Well, yeah, then I let you, Georg, open the buffet.
Yes, so it's my task to say the buffet is open, enjoy the food and eat everything. Nothing can remain here.
Food here at the back, we just need to uncover it. And
yes,
then the
please help us
there in
uncover the
fridge.
food at the back. Just pull off the curtain more or less, the blankets, and then make sure everything gets eaten.
And I would like to call up the speakers on stage. We do a quick photo now. Thank you.
Mouhannad and I already held this talk 2 months ago, and a lot has happened in the field of GenAI for images ever since then. This is a field that's so fast moving, obviously. It's hard to distill what's happening every week, but it's too far away. All right. Okay. So we have tried to distill some of the knowledge that has happened into our talk today. And Mouhannad and we are mainly in the field of machine learning engineering, but also concerned with all the data science stuff. So let's get into it.
Yeah, happy to see many faces today. So today the topic is GenAI for images in 2025. It works, yeah. So before I would like to give an introduction, what is generative artificial intelligence? So it's a new tool of AI tool that is generating new content. It can generate text, it can generate images, videos, and audios. Today, the focus mainly on the images. Maybe in the future we talk about the videos. But image generation started from, it's called 70s, 80s, but at that time they didn't have the technology or the compute power that's needed for that. It didn't get that attention until the 2010, where the deep learning came on the pictures, and many research start working on the image generation. The first well-known model, or the model that get attraction, is the variential autoencoder. The idea of this model is to learn from the data distribution. So it's compress the image to latent representation, and then decode it back to the real image and try to learn the distribution. And the next time, if you get any distribution, try to generate based on the learn that you learned from the distribution. Later in 2014, one famous model came, is the generative adversarial network, where it's used until now. It has very interesting idea. It consists of 2 models. One is the generator, it generates the image, and the other one is a discriminator, which check if the image is fake or real. And then they learn from each other. The generator get better with generating the image, and the discriminator will be better with distinguish between fake and real image. Later in 2016, the auto-regressive came in the picture. This one was taken from the language models, where you have a text and you predict the next text in sequence. So here they are predicting pixel by pixel in sequence. What came next is the diffusion models. Actually, the diffusion models, they were around since 2015, but they didn't get any attention, mainly because the computation power and also they didn't have enough images to train the model. The last 2 years, they start to get high attention, and many researchers, as you see, there are many publications about it, and many products use diffusion model as a backend, like DALI, stable diffusion, Flux, and so on. So how the diffusion model really work? The basic idea that you have a noisy image and you are trying to remove the noise step by step. Sorry for that. You remove the noise step by step until you get an image. But how to do that? You need to follow few of the following steps. First is the forward diffusion. So the forward diffusion, you have your training data. They are a set of images, millions usually, and you can try to add noise step by step until you get fully noise images. At each step here, we need to add, we need to train a model to predict how much noise you added and try to remove this noise. So we train a model to remove this noise at each step. And then in the end, when you get a fully noisy image, your model will start to remove the noise step by step. Those diffusion model can categorize in two different ways. One is the unconditioned diffusion model, so you don't have really control how the image will be generated. You have a noise, and then you will get some output based in your training data. For example, you train your model on picture of cats, then it will generate for you some kind of new cat picture, but you don't have control of the color, what type of cat, and so on. The other type is the conditional diffusion model, where you can control the output by some kind of input. You can write a text and it will generate image based on your text. You can do it for image embedding. Also, you can have multi-prompt, like you can have text and image as input, and based on it, you will have specific output. This is not just for diffusion model, you can apply on any model for GenAI, generative images model, not just for diffusion model, this categorized. As we see for the unconditional, we saw like you have completely noise and you try to generate image, but how, for example, the text to image concept is working. The idea is the following. You get the prompt and you get an embedding from this prompt. So you have a text, you embedding, you get the embedding and use this embedding to guide your denoising. So you get the noise, you try to, based on your input, you try to denoise the step by step and remove the noise and you get the image that you want. Of course, you have a training process where you need to have the pair, I think, million of pair of text and images and try to train based on the composition and the visual concept of the images. To understand more how you are guiding the denoising. So as we said, we have the text, we encode, we get the embedding and the condition vector, and then we can use it, combine it with the current noisy image in some kind of neural network. We can use unit or you can use transformer to predict the noise. And this noise then will be subtracted from the image, from the noisy image, and you get less noisy image. And next step, you will do the same until you get a full new image with the high resolution. Again, going back, sorry for that. Again, this part, they can be used in different, for example, unit, you can use transformer. You don't need to use the noise image. You can use, for example, the latent space and so on. And there are many improvements where Julius will be discussing now.
Yeah, thanks, Mouhannad, for giving us a basic overview of how the diffusion process works. And I want to dive a bit deeper into some technological advancements and architectural milestones that have happened over the last 2 years, actually. A lot has happened over the last 3 months even, and this will be on the next slide, but now I want to dive into these. And I have cherry-picked, obviously, some milestones. It's not possible to tell you about everything that has happened. So I've cherry-picked some stuff that I deem to be worthy. So first of all, the diffusion transformer. I assume that most of you, or all of you, actually know how a transformer works. So I won't get into too much depth on that. So the transformer is mostly known to most of you from language technologies, but it's also used in vision and diffusion modeling. And in this case, it's not words or tokens in a sequence that attend to each other to predict the next token, the next word, next letter, whatever, but rather it's used on images, and these images are being divided into patches, into smaller parts, and these patches then try to find other patches in the same image they find especially interesting. And from that, the prediction that is being made is not the next patch or next token, but rather a denoising step, a noise removal step. That's what Mouhannad already told you about. So this architecture obviously is highly, I say obviously, but it is highly scalable. It comes as a substitution to the former state-of-the-art or the former mostly used unit that you can see on the right-hand side. The unit consists of convolutional layers or convolutional kernels, and the convolutional kernels obviously also were quite a powerful piece of architecture, but they have these two disadvantages to the transformer architecture. The transformer architecture not only is highly scalable, meaning you just throw more GPUs at it and it performs better, but it also provides more long-range context. As I said, each patch in an image can actually find every other patch in an image interesting as much as it wants. And as you can see here, it's not only the patches being fed to the diffusion transformer block, but also a time step embedding. So what's important for beyond the patches themselves is the time step the diffusion process is in at the moment of removing more noise. The second thing on my list is flow matching. Flow matching in generative models. This is a mechanism that has been around for a longer time, but in 2022, it was actually introduced into generative modeling. And this is a very fascinating alternative to diffusion itself. So diffusion, I said this before, but it's about noise removal. You have to predict how much noise you want to remove from a noisy image, from a random noise distribution, in order to get to a target distribution. But in diffusion, this target distribution is not really defined. We only define an objective to remove certain parts, certain noise levels. And this is kind of tedious and redundant, because in a noise removal process, you might flip. I want you to imagine this like flipping pixels, because the computer doesn't know that, it doesn't care how an image looks, if it's like an image that we as humans can understand or not. It just flips pixels. And sometimes this pixel flipping will happen redundantly, like a few pixels will be flipped back and forth. And therefore, flow matching provides this idea of instead learning a direct path between random noise distribution and a target distribution. Something was drawn here. I mean, okay. I don't know if I did this. Fine, okay. Yeah, so flow matching tries to learn a direct path between random noise distribution and a target distribution. So the objective that is being defined to reach a target distribution is actually much more efficient than what's being presented in the diffusion process. The original diffusion process is still powerful and very nice and also highly scalable, but it's redundant and inefficient, and we need something else. So in this flow matching, I have all these visualizations because obviously I know that words alone cannot explain what exactly is happening in this flow matching process. So on the right-hand side, you can see a so-called random noise distribution where we want to sample a target distribution from, that you can see on the left-hand side. And these paths that you can see in the middle are what are being learned by a model, by a flow matching model or flow model. And to even give you more visualizations on this, on the left-hand side, you can see how the diffusion process might look like. Pixels are, as I said, being flipped back and forth, and instead the flow process defines a vector field that goes step by step and leads like flips pixels. As I said, I like this analogy, with a certain velocity into a certain direction to reach a target distribution. And I even have another analogy on this. This is like trying to find your way through, for example, a forest. And you could, for example, use markings by other people that went through this forest to a certain destination. But obviously, a better way to do it would just be to use GPS or a compass and to know where you want to go in the first place. So this is flow matching, and as I said, it was released or already proposed in 2022 for generative modeling, and last year it was actually scaled, or there was a paper was released on this, on the scaling of rectified flow transformers by Robin Rombach and Patrick Esser, who were at that point still working at Stability AI. And a few months later, they went on to found their own company, Black Forest Labs. You might have heard of it, which is the company behind Flux. So you might very well know that this flow matching process apparently made them believe that they can do even better. Okay. Okay, all these like architectural milestones are great, but we need something to control these diffusion models, these generative models. Because otherwise the diffusion model would just generate something. You don't, let's say you don't tell a diffusion model what you want to be generated, but instead you just give it a random noise signal, you sample a random noise signal. It would then try to find the closest or the nearest target distribution in image space that like is possible for it. So instead we want to provide some guidance. It's like giving like an art student a reference material, so the art student can draw something that you actually imagine in your head. I mean, the art student can also draw something, right? But you want to give some reference material. And there are a few control mechanisms, and I cherry-picked this one, the control net. Control net is essentially feeds a piece of information to a generative AI model that makes it like fill in the lines. For example, you want to, let's say, generate a cook, and you give an open pose, a human pose, to the model in addition to your text prompt, then the model will know that it needs to fill the lines of the human pose to generate a cook with a certain like pose. Yeah, as suggested by you. Yeah, that's it. I can go to the next. Yeah, last on this list is the deep compression autoencoder. And I have added this to the list because I think that the autoencoder, or generally the variational autoencoder, is an underappreciated part of diffusion modeling. Because all of these diffusion processes, all of these generative processes can happen so quickly and so efficiently because they happen in latent space. Mouhannad said this before, but what does this actually mean, working in latent space? So if we would work in pixel space, for example, let's say you have a 256 times 256 pixel image, then you would have to work with 65,000 pixels, would have to fill in all of these. And this requires quite some computational resources. So instead we downsize or compress, or let's say reduce the images that we want to generate to a smaller latent space, and we use a compression rate, or have been using a compression rate up to 8 times. So we don't have to work with 65,000 pixels anymore, but rather 8,192, which will eventually speed up the inference process. And now it's okay. And now researchers from NVIDIA have actually found a way to increase this compression rate by even more, like up to 64 times. This doesn't only mean that now our 65,000 pixel model or image can be generated even faster, but now we can actually generate high resolution images with 1,000 times 1,000 pixels or even more. I will get into this also like in 2 slides, but I want to say that NVIDIA, for most people in deep learning, they are known as the company building your GPUs and your computational resources, but they are still a company very much concerned with graphics in general. So this is why they are big in this area as well.
I think you need to.
I don't want to click again. I guess we can't get rid of it. They are telling me how I did it, but I can't redo it, undo it. Okay. No worries.
Refresh the page, maybe. Refresh the page. Let's refresh the page, I think. Yeah. We could use image generation to.
All right. So I went into some, as I said, cherry-picked architectural milestones, but I also want to get into some even more cherry-picked stuff that happened over the last 3 months, especially also since the last time we held a talk like this. So some stuff that has been proposed. These are not things that will work for sure, but I found them especially interesting. And let me start off with noise refine, an idea to that the researchers from this paper proposed that we can, instead of guiding a diffusion model, as I proposed with the control net slide, we could just learn a random noise distribution that is not truly random, but is pseudo-random and might lead to better results, to higher quality results, and maybe even speed up training and inference time. So yeah, they wanted to train some well-defined noise, and the way they did this is they generated images from true noise. So true noise is what you can see on the top left. They generated these images, took an inverse from these images, which is then some pseudo-random noise, and they tried to learn the relation between this true random noise and pseudo-random noise. And they hypothesized that this further mechanism would then lead to an outcome to generation that is less reliant on guidance. And they actually did it. They actually managed to train this model and train on pseudo noise that works better without guidance. And in addition to this, they gave us some interpretability of the diffusion process, namely the pseudo noise distribution has some components that are different from the true random noise distribution, that are very relevant to how you generate an image. And those components are low frequency components. These low frequency components are especially responsible for the structure and forms in images. So they found out that pseudo noise distribution has a lot of these components like differently than in the true noise distribution, and this leads to better guidance. The second paper is rather short, decentralized diffusion. So the researchers from this paper proposed that some true decentralized diffusion process is possible. What does this mean? Truly, this decentralized diffusion isn't it possible to just decentralize and or don't we already do this? Yeah, we do actually already distribute our model training, but we do it with synchronization and with alignment between several resources. So we give some training data to different resources. These resources train their models, synchronize on gradients and parameter updates, and then some monolithic model will emerge from this. But a truly decentralized diffusion training process would look like this. You would have several resources train on several pieces of training data without synchronization. And then in the end, you would put all of them together, use a routing mechanism, and still get output that is on par, as good as the output from the monolithic diffusion training process. And the researchers from this paper managed to do so. They actually managed to train a model in this way that is on par with state-of-the-art models. And this is very empowering to researchers because in universities, hardware tends to be underutilized. So you can just ask, for example, researchers or PhD students, whatever, from different areas in your university to train some part of your model on their GPUs, on their available GPUs, and then gather together what you have trained, implement a smart routing mechanism, and have as good of a model as someone who trains on thousands of H100 GPUs.
Yeah, I think soon we will have torrent-based training.
So this representational alignment, this representational alignment paper is actually one of my favorite because it shows some evidence that diffusion models are also vision models. I mean, this might be obvious because we train on images and the diffusion transformer tries to understand what's in an image as much as a computer vision model does, as a vision transformer, for example. So the researchers asked, why don't we just align the weights? Why don't we use a pre-trained computer vision model and the features from that to align whatever is being trained in a diffusion transformer process or diffusion process? They used a self-supervised computer vision model, to be more precise, Dino V2, which is, in my opinion, one of the most powerful computer vision models out there, was trained by Meta. And it was trained self-supervised, which means that it wasn't given text-image pairs, but rather was trained on images alone and pieces from this image. Something happened again. No, okay, it's okay. So what they did is they used the output from this Dino V2 model on the left-hand side, aligned it with an additional loss term with output from with an early layer from the diffusion transformer. So there's this denoising objective that you can see on top, but in addition to that, they defined a loss term or an objective that aligns these outputs from the pre-trained visual encoder, the Dino V2 model, and the output from the early diffusion transformer block. And last on this list, this is very interesting. The last time we did this talk, I actually proposed that implementing a 1-bit quantization on diffusion models would be a major leap for us to be able to use such models on our own, for example, hardware, on commercial GPUs, or even a CPU. And ever since then, around Christmas, this paper by ByteDance was released on a 1.58-bit quantization of flux. And they used the quantization on only the weights. So they quantized all the weights into 1.58-bit. And by that, reduced the memory footprint by 70% from 22 gigabytes to 5 gigabytes, which is great because now you can actually use the models on commercial hardware, which doesn't mean that this speeds up the inference. And you might wonder why. That's because the quantization was not done on the activation matrices, and those are actually the ones that take so much time in inference. All right, so that's it on the architectural milestones. I just want to do a quick detour on one model that I found especially exciting, NVIDIA's Sana model. As I mentioned before, NVIDIA is a great company in not only GPU or tensor matrix multiplication delivery, but also in graphics in general. So they proposed this model with only 0.6 and 1.6 billion parameters in size. And this especially outperforms pretty good models. I must say, Stable Diffusion 3.5 is not on here, which is kind of deceiving. I want to tell you this. But the generation latency in comparison to FluxDev, SD3, as you can see, is much smaller. And how did they, especially with the 4,000 times 4,000 pixel high resolution image. And how did they do this? They implemented the DCAE, the deep compression autoencoder that I presented before. They used a linear diffusion transformer, which, well, we get around the quadratic complexity of diffusion transformers. Thanks. With only little quality loss in this instance. And lastly, they used a small decoder-only LLM in comparison to normally using like CLIP and T5 embeddings, which take some more space in terms of hardware requirements and inference speed. Okay, so I'm going to hand over to Mouhannad, who's going to talk about some deployment and deployment tips, maybe even.
Thanks again. So let's see. So deployment. The question here, like, do I bring those model and host them and buy a server with I don't know how many GPU and host them myself, or I can use some managed model by some cloud provider or some company and use that model directly with the REST API? To answer this question, you need to make a decision matrix based on many parameters. The first one is the setup time. Do I need something fast, or I have time to set up all the infrastructure? If I want something fast result, then it's better to just use managed model. I get the API, I call it, and generate some images. The other question is the experience needed. Like if I need to host it myself, I need somebody with the expertise to host it for me and manage the GPU and manage all the model. If I don't have all these people and I need to hire them, if not, so it's the best to use the managed model for sure. Also the scalability. So if you need to know how many requests you will get per day, like how many users you will have and how many requests you're requesting. If you have, here is like you need to also make comparison between the scalability and also the cost, because the managed model, they scalable automatically. You don't need to worry about that. But if you have a lot of requests, like you have 1 million requests per day, then it will be very expensive to have managed model. It's better to host it yourself because it will be very expensive to pay for per request. And it's the opposite. Like maybe you have high demand per 1 hour, and then all the day you don't have any requests. So it's better not to buy a server and have all these costs for nothing. The another thing also, the customization. Like when you use a managed model, it's hard to customize based on your need. You need to first test if it's work for you, then it's okay. If not, you need to host it yourself and train the model for your need. Another parameter is also very important, especially for big companies, is the data privacy. So for the managed model, you need to check with the provider what they will do with your data. Mostly they will use your data. And if your data is very sensitive, it's better to use to host your model yourself. Now, what is the key focus area in the AI generative images in 2025? So the most important is the real-time generation or improving the inferencing, and also try to optimize it to work on edge device and also maybe in mobile. Another improvement is the control, as Julius said. So we should have better prompt and better accuracy, and we get based on what we request to get better result. And for sure, the consistency, like you want to have the nice coloring, nice handling for complex scenes, and so on. Another aspect is the ethic and the responsible AI, which is especially in Europe, this is a big topic. you want to have a context safe and also don't have a bias for some kind of image, like not always getting some type of image. You need not to have biased data. And for sure, the content safety should be controlled here. You don't want to have some strange image coming to you. Another thing, also focus on the have real data or real image, which is becoming challenging these days to distinguish between the real and fake. And finally, how we can easily fine-tune and customize the models. Another focus was also start to everybody shift is the video generation. The video generation, maybe you can start here. It's very complex compared to the image generation. We have some music also. I think you need to. Oops. So you don't just work on image, because if you just generate image by image, as you see here, you will have a strange output. Like you need to have control over what you have.
So video generation obviously introduces quite some complexity. It's not only generating single frames, but putting them together. And we could fill another like 40 or 50 minutes just talking about what's happening in this area.
But again, the big provider, managed to solve this issue. And if you can switch, you will see a very, very, very realistic scene. And like, I think it will be when it will be public, I think it will make a very high revolution steps. Yeah.
Also, we have brought this quick slide. I just wanted to ask you if you could differentiate which images on this slide are actually fake and which ones are real. Someone wants to give it a try.
You have two fake. Make it easy.
Spoiler. First and last are fake. Okay, very good. So the house is actually fake, and the second one is also fake. I think with the house, you were still able to spot that the fence looks kind of wonky, and in the second picture, you might also see that this whatever is in the background is just something that it's not like a tractor or whatever. It's just a blob.
I think they played with the color, maybe.
The first one is actually real. I took it myself. No, I'm kidding. So, yeah, we've come to the end of our talk about generative AI. As I said, we could fill another hour with talking about video generation, and then also how diffusion models or diffusion processing is used in language modeling, for example, in the meantime. But I think we've tried to distill some of it down to what we've presented. Thanks for listening.
Thank you, everybody.
I see Georg is already there. We have time for questions. Georg, Rahim.
Thank you for the nice presentation. I have 3 questions on the pseudo noise first.
On the what?
This one, the noise refiner.
Right.
Pseudo noise. I didn't get that actually. That reminds me of flow matching, right? Because the problem with the DDPM was that we didn't get to the pure noise, and they are actually finding the way to do the flow matching. Is that right?
Yeah, so the idea is to find a smart way to sample the noise, to not like begin with the target distribution, but to find some noise that's easier to work with. That was the point.
But is this better than flow matching? What's the point?
I would not say. I would not say it's better than flow matching, but it's just some idea that was implemented.
What made you interested in this if this is not better than? Just out of curiosity.
You can have a real, start with noise that it will help you with the output that you want. So you don't have a random noise. So you have from beginning, you have fixed noise that you can help you with the generate the image that you want.
No, the point that made me interested in this is the low frequency components they found to be especially interesting for generation. So I was concerned with interpretability of the diffusion process, and this gives us some interpretability of what's happening.
Okay. The second one is the next one, actually, the distributed one, right? Yeah. The right one is not trained from scratch, or is it?
It is.
And they showed that it's possible to train multiple diffusion models from scratch
on different portions of the training data, and then they put them together and
What
route.
do you mean by putting together? It is like averaging?
No, it's like a routing mechanism to choose it's not like mixture of experts. It's like an actual experts model, like where you actually route to the one expert that generates the best image.
Nice. Thanks for sharing. I was not aware of these papers. And the next one is alignment. Is this better than the previous methods? What's the catch here?
So it speeds up the training. It's not better, but you can speed up the training, because if you align and have a further loss term that pushes the model into the right direction during training more quickly, then we can save some time on training, just save time on epochs.
And could they show that it's better than stable diffusion or a large
So
scale?
the results were on par with state-of-the-art models, but the training speed up was especially exciting.
Cool, great, thanks.
More questions, anyone? Well, if there are no questions, we can thank our speakers. We are on time. I think it's the first time in the history of this 64 edition deep learning meetup that we stuck to the agenda, the schedule. Thanks, Mouhannad. Thanks, Julius. And thanks also to Adam, our first speaker. Thanks everyone for coming. I have to announce only the next meetup. Do you have any other final word? Well, let me do that first. Yeah, we roughly do this meetup monthly. We were a bit late. Our last meetup was in November. So thanks for coming today and sticking with us. The next meetup is though next month, pretty exactly on 19th of March at Dynatrace at Hauptbahnhof. So hope to see most of you there again. We're going to have exciting topics again. But we don't have any speakers or venues after that, so for April. So if you know exciting topics, if you are working on something super exciting yourself, please let us know. If you came across some interesting paper or interesting speaker, also let us know. And if you can host roughly 100 people for a meetup in the evening, also let us know. Contact at vdlm.at, I don't have the slides anymore, was our address. But yeah, simply talk to us. We're still here. Yeah, Georg will tell us in a moment when we are getting kicked out, but I hope we still have some time for more networking and a few drinks left. It doesn't look that good, but
No,
yeah.
we have still drinks left. It's like some are in the fridge and cool, some are not cool. So if you want to drink more, you have to put them into the fridge yourself so they get cool. Really good, thank you. You will not get kicked out too soon. We still have some time left here. Enjoy the evening, drink the drinks. I guess this is where the event ends for the people in the stream, because there are no drinks in the stream online. And the next time when we meet here in T Center is on the 9th of April. We will have have opportunity to host the data engineering meetup. In fact, that time also Magenta or some colleague and I will talk here about how we are dealing with data at Magenta.
Okay, I want to thank also Alex and Pavel, who are here as organizers together with me tonight. And thanks again to our speakers. Big applause, because the meetup wouldn't be the meetup without our speakers. Thanks everyone, and have some good conversations in this last final networking part.